Hi everyone, welcome to the third lecture on linear programming. I should say third video. The first two videos, I know I kind of scheduled it as the first lecture and the second lecture, but really they're all kind of equal parts. This one might actually even be a little bit shorter. And so we're going to treat all these three lectures, all these three videos as kind of in total, the two lectures on linear programming. Since we're posting them all online anyway, these three will count kind of as the two lectures. So this lecture we're going to talk about duality and the dual simplex. Duality is one of these foundational notions in convex optimization that comes up all over the place. And we're going to introduce it here largely in the context of linear programming, though we'll give some hint to the more general case as well. And we'll specifically talk about how it relates to the simplex algorithm, both in terms of this dual simplex algorithm, which is actually a different kind of simplex based upon duality, but also we're going to use properties from the simplex algorithm to actually prove things about duality in the case of linear programming, or at least prove them informally, and that'll kind of be the method that we use. Okay, so let's jump right into talking about duality in linear programming. So as I was saying, duality is an extremely powerful concept in convex optimization in general. We will consider the general case, but we're really going to focus on it for the most part on linear programs. So let me introduce this in the following way. Let's say that we're given a standard linear program here. So again, minimize over x, c transpose x subject to the constraints that ax equals b and x is greater than or equal to 0. For this problem, we're going to define a new function called the Lagrangian of this optimization problem. We're going to use script L to denote the Lagrangian. And the Lagrangian depends on the original optimization variables x, but it also depends on two more variables, y and z, that I'm calling here. And these are known as the dual variables of the optimization problem. These are called dual variables, or of the Lagrangian in this case. They're called dual variables. And what we do is we take the objective. So the Lagrangian contains the objective term, which is the same as this term here. But then it also contains two more terms, one corresponding to each constraint in our linear program. So if we just take this term here, and we're actually going to think of writing this as ax minus b equals 0. We're going to take this ax minus b portion, and we're going to have a term that is equal to that. Then we're going to take the term in the Lagrangian will be the inner product of our dual variables y and this equality constraint representation here. All right, so it's this, again, this is the inner product. This whole term here is just a scalar, but it's the inner product of our dual variables y and our equality constraint ax minus b. And then similarly, though there's a negative sign instead, we're going to take the inner product of our z variables, our z dual variables, and our inequality constraints here, which in this case the inequality constraints is just the x vector, because we just have the vector x in our inequality constraints. And we're going to actually have a term which involves the inner product of this term and our inequality constraints. So in this here, variable y, which is of dimension m, remember a in LPs is considered to be m by n. So this whole term here is an m-dimensional vector. And so to make the inner product kind of work, you need to have y also be a m-dimensional vector. And z is an n-dimensional vector here, because, of course, we're taking the inner product of z and x is n-dimensional. So this defines the Lagrangian of our optimization problem. So why is this an interesting function? Well, to start off with, and I'll actually come back to this slide, I think, when I write this, or I might just write this thing again. The first thing to note is that if we maximize our Lagrangian over the dual variables y and z, where we're unconstrained in our maximization over y, but we can only pick z values greater than 0, if we maximize the Lagrangian over these dual variables, then, and it's important, notice I'm saying it's not maximize here, but the term actually is max. So this means the actual optimum value attained by this maximization problem. This will be equal to c transpose x if, and really if and only if, the constraints of the linear program are satisfied, i.e. if ax equals b and x is greater than or equal to 0. And see why this is the case. It's actually pretty easy to see. And if these constraints are not satisfied, the solution will actually be infinite if they're not satisfied. So this is actually pretty easy to see why this is the case. Let's just consider our Lagrangian here. Our Lagrangian is equal to C transpose X plus Y transpose AX minus B minus Z transpose Z. So Lagrangian is equal to this thing. And think about this term here. If this term here is not equal to 0, right, i.e. our constraints are not satisfied, then when I maximize my Lagrangian over y, I can choose y to just be equal to this thing, but then some large multiple of this thing. I can scale it. I can choose it in the same direction as ax minus b, but then scale it to be some large multiple of that. And in doing so, I can make the Lagrangian term as large as possible, right? So the only way that the maximization over y will not be infinite, i.e. I can't just do that, is if this term, in fact, equals 0. So if it equals 0, then I, of course, cannot make it as large as possible by picking a value of y. It doesn't matter what value of y I pick. It will always be equal to 0, this whole term. Something very similar, of course, happens in this case, in the case of this term here. So let's suppose that there is some xi less than 0. Then by picking zi, that term zi, to just be some big number, this whole term here becomes arbitrarily large, right? We're subtracting it, so xi being less than 0, that would mean it is negative, and zi being large positive, I should say big positive, would make this whole thing very, very large. And so again, if there's any term xi less than or equal to 0, strictly less than 0, doesn't actually matter how much less than 0, but it's strictly less than 0, we can make this whole thing infinite. So the only way that this maximization here, the objective of this maximization problem, is not infinite is exactly if we satisfy the constraints. Okay, and this is kind of, honestly, kind of a trivial thing, right? Because it's just, we're sort of defining it in a way that is setting this up. Notice that this is also why the zi's have to be greater than 0, because if there's some xi term here, strictly greater than 0, that's okay by our problem. But we can't make the thing as big as possible by picking a zi, because the zi's have to be themselves greater than 0. So this only works if the xi is non-zero and actually strictly negative. So what this means is we can actually write the original problem in kind of an interesting way. You wouldn't think about writing it this way, but it's a perfectly valid way of writing it. We can write it as minimize over x, this thing here, which we know is just equal to our objective if the constraints are satisfied, and infinite otherwise. And so of course, since we're minimizing over x here, we don't want the objective to be infinite. And so we want to minimize this, i.e. subject to our constraints being active. In other words, this is just equivalent to our original linear program. It's a sort of a pure optimization, or a pure kind of a pure way of writing the optimization problem without writing the constraints separately, kind of embedding the constraints into the optimization problem itself, or the objective itself. Just the thing is you have to use this min-max terminology now. So basically we're using the same min-max terminology here to express the same problem as in standard form. So that's nice, but it's not that useful, right? Because it doesn't seem to be that useful yet, because all we've done in some sense is just sort of rewrite our problem in a similar way that seems kind of trivial, right? Because this discussion didn't tell us what z should be or what y should be in any really meaningful sense. It just sort of told us a way of redefining our objective. But the thing I want to introduce now is a modification of this problem here. So what we're going to do is we're going to take this and we're going to swap the order of the min and the max here. All right, so we're going to first do the maximization and then the minimization in this order of things. And I mean, so far it isn't really clear what this is doing. But doing this kind of swapping of min and max optimization order is actually a really important thing in the context of convex optimization and linear programming. So let me sort of dive into that a little bit. So I'm going to call P star here the solution to our original linear program. P star is just really, so P star, I could write it like this. I could write P star is the min over x. So it's the actual objective value, but then x sort of subject to x subject to ax equals b and x greater than or equal to 0. A little bit cumbersome, but I'll write it like that, of c transpose x. So this is our objective, our optimal objective to the linear program. And I'm going to write d star as the optimal objective to the other order here. And this order here, just going back one slide, this order here is actually called the dual problem. So d star is the optimal solution to the dual problem. And I could write it this way too. I could write it similar as I wrote up here, but I'm just going to actually write it. D star is the actual objective. It's the max of the min of our Lagrangian. And so we're going to call D the dual optimal solution. Now we have sort of immediately a really nice property, which is that D star is less than or equal to P star. And this is actually sort of just follows kind of from sort of very basic logic here. The idea is if we minimize over x first and then maximize over y, so if we do it this way, minimize over x first and maximize over y, this is always larger than maximizing over y first and then minimizing over x. Basically the sort of the player that gets to move second also always has the advantage because they always already know what the values of x are. And so doing it in this order will always lead to a larger objective than doing it in that. And doing it in this order here will always lead to a larger objective than doing it in this order. So that isn't that interesting, actually. That sort of says, whichever player goes second has the advantage because they already know what the first person did, what the first sort of player did, be it the max or the min player. But there is this sort of remarkable property. So for linear programs, and actually for a large set of convex problems, but we'll just talk about it here for linear programs, we actually have P star equals D star. In other words, the dual optimal objective is equal to our original optimal objective for our optimization problem, P star, sometimes also called the primal objective, because we call the original problem, in the concept of duality, we call the original problem the primal problem. And this is actually kind of an amazing thing, because there's no a priori reason to think that if you swap the order of things, you wouldn't somehow give an advantage to one player or over the other. But what this is saying is that it actually doesn't matter which order you go in for a linear program. The optimal solution will be the same. So I can first maximize over the dual variables, then minimize over x, what are called the primal variables, or I can minimize over x and then maximize over y, and these work the same. Now, another crucial property, though we'll talk about this one less, is that any feasible solution to the dual problem actually provides a lower bound on the optimal primal solution, right? Because if there's a feasible solution to this problem here, and by the way, feasible just means that, actually we'll talk about what feasible means in a second when we talk about the dual problem in a little more detail. But basically, if I can find any solution to this problem here, which satisfies the constraints of the dual problem, then actually this will actually give us, because this is any feasible solution will actually be, because we're maximizing over this thing, then any other solution that we have will be even lower than that. So, a non-optimal solution will be lower than this. That means that any non-optimal solution to the dual problem is actually going to be a lower bound on the original primal solution P. Though we'll talk about that more in a second. I'm just kind of alluding to that for now. Okay, so in order to do that, I actually want to now describe what the actual dual problem is for a linear program in standard form, because before I sort of was just describing it in this abstract terms, of these min and max terms, which are not always the most, not always the easiest things to say. So remember, our dual problem is max. Let me actually do this in red. Dual problem is max over y and z greater than or equal to 0 of the min over x of my Lagrangian. I won't bother writing it out here because I have it right down here. So minimum Lagrangian xyz. So in order to make this is great, but just like we didn't like to have the primal problem specified in this form, or it wasn't that intuitive, we actually want to express the dual problem in a form that looks more like our original linear program. And so what we're going to do is we're going to analytically solve for this part here. We're going to solve for what that is, what the minimum over x is for given values of y and z. All right, so let's look at this. So we want to minimize over x of this thing, where here y and z are specified in this minimization, which is substituting in Lagrangian now. This is equal to the min over x of this thing. So now, just like in the original Lagrangian formulation, if certain things weren't satisfied, we could always sort of make this trivially equal, in the case of the other one, positive infinite. But in this case, we're trying to minimize it. And if certain conditions do not hold, then this thing is easy to make infinitely negative, right? So for example, if I just pick some random values say I pick some values of, say I pick y equals 0 and z equals 0. So say if I pick y equals 0 and z equals 0, then these two terms kind of fall out. And I can of course pick, as long as c is not equal to 0, which is kind of a boring problem. If c equals 0, it's I know the solution to the LP, then it's just 0. But if c is not equal to 0, by optimizing x here, I can make x's, there's no more constraints, so I can make x's I can make the objective here, this thing, as small as possible. In other words, I can make it equal to negative infinity. All right, so let's back up a little bit. Let's erase those things. Not have these be equal to 0. How do we ensure that the objective of this thing cannot be made arbitrarily negative? Well, the only way to do it is let's look at the terms that involve x here. So the terms that involve x in our Lagrangian are, we have a c transpose x. We have a plus y transpose ax. I'm going to ignore the terms that don't involve x here. And then we have negative z transpose x. So we want to minimize this thing over x. So this is a linear, and I can also write this, by the way, as, let's see, I'll write it as a transpose y plus c minus z, all inner product of this and x. And so just like before, as long as this thing is not equal to 0, I can make that as negative as possible. And so as you see on the slide here, which you've probably been seeing what I'm building to at this point, the only way for this whole thing to be non-infinitely negative is if this thing equals 0. This whole thing here has to equal 0. And if it does equal 0, then we know that this term in the objective, these terms in the objective here, are all equal to 0. And so the only term left, which I left out before, but the only term left in the objective of the Lagrangian was this b, came from this guy and this guy, so it was negative b transpose y. And so this term is the only one left. And so, of course, now I've built to what I have on the slide here anyway. But the idea is this whole minimization is going to be negative infinity unless this thing is satisfied. So it requires this thing to be satisfied. And if this thing is satisfied, then it's equal to negative b transpose y. So what's really interesting here is that we can actually write this as another linear program. And so the problem is, remember, our original problem is to maximize over y of this thing. But now we know that this thing is equal to this, negative b transpose y, if a transpose y is plus c, and z is equal to 0, negative infinity otherwise. So we can actually write our dual problem kind of in the form of what looks like a linear program, right? So we can write it as, I want to maximize over y and z, subject to first that z equals greater than equals 0, because that was one of our original constraints here. That was an original constraint we had in our problem here. Subject to that constraint, but also the constraint that a transpose y plus c has to equal z. Because if we don't satisfy that, then our problem is negative infinity, and so since we're trying to maximize our objective here, we wouldn't want that to happen. In other words, we have to satisfy the constraint. And by the way, just as a matter of sort of convention, this term here, these two terms, can be simplified a little bit, right? So if we're, because these has to be greater than 0, so that means this whole thing here can be anything, but it just has to be greater than 0. And so the way we typically write this is actually as maximizing negative b transpose y. The objective stays the same, but we write this combination here as just the fact that negative y, a transpose y is less than or equal to c. And if you remember, this is exactly a linear program in inequality form. Right, so we had the standard form, which had equality constraints, and the only inequality constraint was x is x is greater than 0. But we can write the dual problem, and of course we can convert between the two as much as we want, but the dual problem can be very naturally written as a linear program in inequality form. So this is sort of an amazing thing, right? Because we've taken this program, which is sort of looked here in sort of a very non-intuitive way, and we've expressed it, the dual problem itself, as a linear program. Okay, so now I want to really prove, actually, the main theorem about duality for linear programs, which is, for linear programs, strong duality holds. In other words, our objective of our primal problem, which again is the minimize over x formulation, or really the min over x because the objective value, is equal to the dual objective value, which is just the solution to this problem here. The objective, the optimal objective of the solution here. And what's also really cool, actually, is that the simplex algorithm actually provides both optimal primal and optimal dual solutions. You can from the solution you get from the simplex, you can actually extract both these two solutions. And it's actually very easy to see once you look at the simplex algorithm itself and what the terms are that are involved in the simplex algorithm really mean. So it's this is the end of the proof. There's a missing, I guess there's a missing QED here, but there should be a little QED here. So it's very simple. When the simplex algorithm terminates, we have two conditions. The first is, so number one, we have the fact that x subscript j, or x script j, subscript j, is equal to a subscript j inverse times b, and this term is greater than 0. And in fact, remember, this is just sort of, you always pick x according to this. But at the optimal solution, this, at the end of the simplex algorithm, we know we actually have the optimal solution. So I'm just going to write it as x star subscript j equals this, greater than 0. Oops. And by the way, all the other terms in x star are equal to 0, the ones like this. So this equal to 0 here is just that actually is a term that's always maintained in the simplex algorithm. So that actually is those terms at every iterate are greater than or equal to 0. But the optimal solution, we also have this at the optimal solution. So this is equal to a inverse script j times b. So we also, though, have another property. We also have the property that the c bar, oops, let me hide the whole thing, c bar, which was our cost decrease, which is equal to, and I'm going to write it, I defined before kind of c bar j for each individual j, but it's pretty easy to show that this is also equal to c minus a transpose, a script j inverse transpose, so that's the transpose of the inverse, times c script j. That's just the vector form of these c bar j terms. This thing has to also be equal to 0 when the simplex algorithm, unlike this one, which was true for the entire iterations, this one here is only true for the last iteration of the simplex. It means that there's no direction we can take that will actually decrease the cost of the solution, and so we are done. We've found an optimal, a globally optimal, we know, solution to the linear programming problem. So here's what I'm going to do. I'm going to just take, I'm just going to define, and this seems a little bit maybe magical, or it seems at least mysterious how I'm picking this, but really actually when you look at the things that hold at the solution, you see this sort of has to be the obvious choice for the dual solution. I'm going to choose my optimal dual solution to be equal to, basically it's this term here. It is this part of the term here. I'm going to choose it to be equal to a subscript j inverse transpose times C script J. So that is, again, if I restrict my A matrix, I select the columns corresponding to the active set script J. I look only at the vector Cj on those elements, and I set Y to be equal to this matrix. This is going to be an n by n matrix, so I transpose it, I invert it, multiply it by this thing, and that's going to give me my optimal solution Y star. So if we define Cj like that, then our optimality condition, or the fact that we terminated this linear program here, or the simplex algorithm, really just means, I mean, I'm just rewriting this now, it really just means that C plus A transpose Y, I mean, remember we're defining A to have a negative, or Y to have a negative sign here, so C plus A transpose Y is less than or equal to 0, or in other words, just writing it one more time, C transpose Y star, negative C transpose Y star is less than or equal to C, which was exactly the constraint, going back 2 slides, that we had, or 1 slide, on our dual problem. Okay, so in other words, this solution here that I'm defining, Y star, this satisfies the constraint of our dual problem. And secondly, we know that P star, which was equal to C transpose X star, which equals, from this part here, which equals C subscript J, because again, all the other x's besides the ones with script J are equal to 0. So it equals C subscript J times A inverse B. That comes just from how we actually compute what that solution is, X star. And now this term here is just equal to negative Y. So this equals negative Y star transpose B, which is exactly the objective we have of our dual problem. This thing is just equal to D star. And again, remember, this was in fact just our dual objective. So what we've shown is that this solution for Y, so let's highlight it a few more times here. This solution for Y is both dual feasible, and when we plug Y, this value of Y, into our dual problem, we get an objective here equal to P star. Okay, so this D star, or rather this objective value here is equal to our original objective value. We know that for any setting of our dual variables, of course, this is going to be less than. We're always going to have D star is less than or equal to P star. And in this case, we actually have equality here. So because they're the same, we actually know that in this case, D star equals P star. In other words, strong duality holds for linear programs. And this is sort of a very, it's a very kind of constructive proof. In other words, that we are, specifically giving what the dual solution is. But what this is showing at a bigger, and in fact, we're showing not only that what the solution is, but that we can easily find it from the simplex algorithm. But at a higher level, what we're really showing is that for these linear programs, we have strong duality. And so the dual optimal solution is always equal to the primal optimal solution. Now let's consider I just want to very briefly highlight the more general case of duality. So there actually is a much broader theory of duality than just for linear programs. And I'll define this very simply here. I don't want to get too much into this because we don't deal too much with general constrained convex optimization in this course. But we can actually can just very briefly here define a more general version of duality. So if we have our problem of minimizing over x some arbitrary function, arbitrary convex function, say f of x. Actually, a lot of this holds even for non-convex, but let's just assume that we're talking about a convex problem here, subject to some inequality constraints and equality constraints. And for this whole thing to be convex, actually these functions need to be convex here, and these functions actually here need to be affine. But let's not worry about that too much. Let's just think about a general optimization problem. We can define the Lagrangian in a similar way. So we define the Lagrangian in terms of some dual variables, y and z. And the y terms multiply the equality constraints, whereas the z terms multiply the inequality constraints. And just like before, we have the same property before that the Lagrangian, sorry, I should actually say that this is actually a little bit incorrect here. This should really be the max of the Lagrangian over y and z greater than or equal to 0 is equal to f of x if x is feasible and infinity otherwise. Because again, if one of these terms, for example, and now we're, in this case, let me use a different color for that. In this case, these terms are going to be greater than or equal to 0, so we have a positive sign here. But if any one of these, if any one of the GI inequalities is greater than 0, then I can make this whole thing infinitely large by just choosing z greater than 0 to be really big. Similarly, if any of these is not satisfied at all, the h's, I can make this thing infinitely large by just choosing y to be the same, you know, any term is the same sign as that one term hi. So we have this as before, and therefore we have the fact that our original primal objective can be written as minimize over x, this term here, which we know this term here is just equal to our original objective of our optimization problem, assuming these constraints are satisfied. So we can write our original primal problem as this. And it actually turns out, though I won't go into it, it turns out that it is the case that P star is always bigger than or equal to an equivalent dual problem you can form for general problems. And it is for not all convex problems actually, but for a certain class of convex problems, they have to have things like they have to have a strictly feasible point and things like this. But those are sort of technical conditions. For most convex problems you will encounter in practice at least, you also will have this strong duality. So you actually also would have the fact for convex problems that P star equals D star. But I'm actually not going to focus on that. What I'm actually going to focus on instead is a set of optimality conditions that this duality sort of lets us get in the case of general convex problems, and this will actually will return to the linear programming case with these same conditions. So, okay, we know that this problem here, this sort of function, this Lagrangian, the maximization of the Lagrangian over this thing, is if we minimize that over x, we have our original objective. So what this means is that in order to have an optimal solution, and actually in order to have an optimal solution, both in our x variables and an optimal set of primal variables, but also an optimal set of dual variables, we need to have two things hold. We need to have our objective value, f evaluated the optimal solution, be equal to the Lagrangian evaluated the optimal solution for all these variables, right? Because if this was not true, then we'd be maximizing this thing over y star and z star. So this thing, if this does not hold, we could make this thing larger and infinite by making these larger, and so therefore this is something that has to hold for any optimal solution. The second thing that has to hold is that we need the gradient of the Lagrangian to be equal, the gradient with respect to x of the Lagrangian to be equal to 0, evaluated at this optimal point. The idea there is that if this wasn't the case, we are minimizing this problem. Remember, our sort of Lagrangian formulation is kind of an unconstrained formulation of the problem. So if this is not equal to 0, then there would be a direction we can move in which would decrease our cost, our objective value, and hence would make this not an optimal solution anymore. And so we need this gradient condition to hold to be equal to 0. So what this leads to, actually, these conditions, along with sort of the simple constraints in optimization, actually lead to 5 conditions known as the Karush-Kuhn-Tucker conditions. And they provide necessary and sufficient conditions with maybe some slight technicalities which we aren't going to go into here, like, again, strict feasibility, but those aren't really that important. They provide necessary and sufficient conditions for an optimal solution to general convex optimization problems. So there's 5 of these conditions, and they really fall out directly from these notions that we talked about so far of the Lagrangian. So the first 3 are actually very simple. The first 3 just says that all my GI constraints have to be negative. Remember, that was our formalism, was that we were minimizing, our constraint was that each GI had to be less than or equal to 0. Our constraint was that each hi had to be equal to 0, and our constraint on the dual problem was that the z's had to be greater than or equal to 0. So these are just really just the feasibility constraints, the feasibility of both, in the first two cases, the primal problem, and the second case, the dual problem. The fourth and fifth, though, were kind of interesting. So the fourth and fifth, actually the fifth one I'll deal with first. The fifth one actually is just this condition. So if I take my Lagrangian, and I'll write it actually for both the fourth, thinking about both fourth and the fifth constraint, but write my Lagrangian as the equals f of x plus the sum from I equals 1 to m of zi gi x plus the sum from I equals 1 to p of hi, I did it in the same order actually, of yi hi x. The gradient of this whole thing is just equal actually to this thing. I mean, it's almost just definitional, right? This term depends on x, this term depends on x, this term depends on x. So when you write gradients, you would just push those gradients through the sums and through everything. And that would be the condition that this whole gradient, so this equation here is the condition that this whole gradient is equal to 0. This second term, though, or sorry, I guess the fourth term, is actually quite interesting. So I want to talk about how this evolves. This is called the complementarity condition. And the way it comes about is actually just from Lagrangian well. It's very simple how it comes about. Remember, we had to have at optimality at least, so I won't bother putting them, but if I put x stars in all of these, it's kind of hard to write on this pad with them. But this thing at optimality has to equal f of x. So in other words, this term here has to equal 0. Let me get a different pen color, actually. This term here has to equal 0, and this term here has to equal 0. This one equals 0 kind of, this first one here equals 0, or second one rather, equals 0 kind of obviously, because this term is equal to 0 for all hi. That was just our constraint, the set of equality constraints. So it actually doesn't matter what yi is. It can be positive, it can be negative. It will still be equal to 0. This term here is a bit more interesting, because this term here, there can be gi's which are strictly less than 0. So this is just less than or equal to, but we could of course have a gi that's strictly less than 0. And we could have a gi is less than 0. We could have a zi term. This term says, this one here says that zi's have to be greater than or equal to 0, but we could have a strictly positive zi term here. And so it's not obvious why this term here has to be equal to 0. So the reason for this is that we know, sorry, it's not obvious how to make this term equal to 0, or that it is. Now we know this term has to be equal to 0 though, because this term is equal to 0, and this thing has to equal f of x, so this term here has to also equal 0. So now how does this happen, this thing is equal to 0? So we know actually, so we know that this sum has to be equal to 0. But actually even more than that, we know that each term in the sum also has to be equal to 0. And the reason for that is every gi is less than or equal to 0. Every zi is greater than or equal to 0. So each term, each sort of product here, is always less than or equal to 0. So they're always negative, right? Because they're a product of two things with opposite signs. And so because of that, and they all have to be strictly, I mean, they're all non-negative, right? They're all less than or equal to 0. You can't have a positive one. You can't have zi and gi have the same sign here. So what that means is, in order for this whole thing to be equal to 0, actually each individual term in this has to also be equal to 0. And what this means is kind of interesting, right? So what does it mean for that thing to always be equal to 0? Well, it means that if there's any gi strictly less than 0, that's okay, right? It's fine to have someone strictly less than 0. But in order for this product to be 0, that implies that, I guess I should really write stars here, because this is important. This happens at optimality. Zi star has to be equal to 0. And similarly, if zi star, if the dual variable would be greater than 0, which again can happen. That can happen by our third constraint. But this implies that gi of x star equals 0. So in other words, if one of the equality constraints holds with strict inequality, the other dual variable has to be equal to 0. And if one dual variable is bigger than 0 with strict inequality, then the constraint has to be tight. It has to be exactly equal to 0 instead of greater than 0. And this is why it's called the complementarity conditions. It means that you either have one or the other. And it's a really interesting property and an important property of convex problems in general. Now, let's actually look at these in a little more detail for the case of linear programs in particular. So for linear programs, if we take the KKT conditions and just write out what these are for a standard form linear program, it should be a standard form linear program. They take the following form. X is greater than or equal to 0. That would be my inequality constraints. AX equals B. That's my equality constraints. Z is greater than or equal to 0. That's my dual variable constraints. X dot y, but here this is called a Hadamard product. It really just means element-wise multiplications. But what that means is that for all I, xi times zi equals 0. So here 0 is actually a vector of all zeros, and this is element-wise multiplication between x and y. And if we take the gradient of the Lagrangian, so maybe I'll just write this here. So again, the inequality constraint vector was just x. The dual variables are y, so their product is equal to 0. So that just says that x Hadamard x Hadamard z equals 0. And then my Lagrangian here was just equal to in blue actually. Lagrangian here for a linear program was just equal to C transpose x plus y transpose a x minus b minus z transpose x. So if I take the gradient of this thing with respect to x, I just get c plus a transpose y minus z. I know this thing has to be equal to 0, given this is my gradient condition for my on the Lagrangian with respect to x. And remember, this is actually exactly the constraint we had. Constraint in the dual LP. So these 5 conditions have to hold in order for a solution to be optimal for a linear program. And what's interesting about this is actually a set of nonlinear equations. In particular, this equation here, the complementarity condition, is nonlinear because it involves a product of the dual variables z and the primal variables x. So these equations, they're linear in either the dual variables or the primal variables if you consider the other being fixed. But when you consider both of them, it's a set of nonlinear equations in both these things. But if I just find some solution to the nonlinear equations, I also will have solved the LP. So you can also actually view the simplex method as looking for a solution to these set of nonlinear equations. Now, a priori, there's no reason to believe that you could tractably always find the solutions to a set of nonlinear equations. That can be arbitrarily hard, and it might not even exist. But what we've actually shown by other means here is that in the case of linear programs, there is such a solution, and for example, the simplex algorithm will find that solution. Now, it actually turns out that the state-of-the-art current methods for solving LPs is typically, there are some reasons to use the simplex, but for the most part, if you just want to solve one large LP, it's usually better to use methods called interior point methods. And without going, we're not going to cover these in any detail, but without going into that in any sort of real fashion, what these methods do is they just consider, rather than thinking about the problem itself or the simplex method or anything like that, they just consider these nonlinear equations, and they actually use Newton's method to find a solution, a root of these nonlinear equations. And as long as you find that, you've solved the system, so they do it that way. There's a lot of tricks that are involved there because this complementary condition, for example, it's sort of very nasty. The product being equal to 0 if as long as 1 equals 0 doesn't tell you anything about the other, so they actually use a smooth version of this where they set this to be equal to some constant t times 1 and then take t going to equal to 0. Those details are all sort of not things we're going to cover here, but just so you know, this actually is the state-of-the-art method for how you solve these things. It's just looking at the KKT conditions and then using Newton's method to solve a modified version of those as you go. Okay, so the last thing I want to talk about is, very briefly, I want to mention the dual simplex method. And I'm actually not going to derive it in anything close to the form that we derive the primal simplex in. I'm just going to give the high-level view here and then illustrate a case in which we might want to actually use it and why this is actually useful. So at a high level, now knowing what we know now about duality, I kind of want to describe what the simplex algorithm is doing at some sort of, in some conceptual way. So at a high level, what the simplex method is doing is that at all steps, it maintains a primal feasible solution, right? So at every step, because x is always bigger than 0, and we always have ax equals b for every choice of x we have along the way, we are always maintaining a solution that is feasible for the primal linear program. And what we do in some sense, one way to think about what we do is, we adjust that solution until we cannot find a direction to decrease it. But if we define this variable y now as a dual variable, and this, remember, goes back to actually, if you want to, if you can't quite remember this, you can go back to the way we prove that the simplex algorithm finds a primal and dual optimal solution. The idea is we're trying to find some point where this solution y is actually dual feasible as well. So in other words, and this thing is actually just the sufficient decrease condition, so rather actually this thing being A transpose y less than equal to C, that is actually equivalent to the condition that C bar J is greater than or equal to 0. And you can go back to the proof about the simplex algorithm if you don't remember that. So what we're doing is we're maintaining a primal feasible solution, and we're adjusting the solution until we also have a dual feasible solution. And once we have both primal and dual feasible solutions, this is actually exactly what the KK conditions can say, we've solved the problem. Once we have both those two things, if a solution that's both, or a pair of solutions that's both dual and primal feasible, we solve the problem. Now, there's an alternative approach that just mirrors it's sort of the opposite of this thing exactly, where you actually maintain a dual feasible solution, i.e. you maintain some y always equal to negative a subscript j inverse transpose cj, such that you have this. Okay, we'll show in the next slide how you do this. We're not going to derive it exactly, but we'll show how you do this. And we adjust, we make moves kind of in the y space such that our resulting primal solution, which is just, again, x subscript j equals this thing, is actually primal feasible. It's greater than or equal to 0. And this method here is called the dual simplex algorithm. So you can derive it actually in the exact same way, thinking about adding terms to your basis, etc. You can derive it the exact same way we derive the primal simplex algorithm. I'm not going to do that. If you want to try to do that on your own, that's actually a very good exercise to make sure you understand these things. I'm just going to give you the final sort of snapshot of what this does. So what the dual simplex algorithm does is it requires that we start at a set of indices script j such that y equals this thing, such that for y equal to this thing. This is sort of my dual candidate solution. It satisfies negative a transpose y is less than or equal to c. Now, of course, how you find that first feasible solution? Well, that was the same problem, for example, in the primal simplex of how we found some set of indices j, some basis j, such that our resulting x was strictly greater than 0. It turns out, it's in the general case equally hard to find this as it is to find the case where some xj, x script j, script j equals a script j inverse b. That, in our primal case, had to be greater than or equal to 0. So it's in theory, it's no easier to find this set of indices here than it is to find this set of indices here. But in some cases, finding one is easier than finding the other. So this is actually, we'll get to this in a second, why this is true. But basically, there are cases where it's easier to find this thing than it's to find this index j. And actually, just like we did for the primal simplex or for the normal simplex algorithm, you can always construct an augmented LP that will help you actually find the solution here. And in fact, you can always convert this to something in standard form anyway. So it's easy to find this if you really want to. Okay, so now what we're going to do is we're going to repeat the following. So first, we're going to let x equal this thing. So we're actually going to form our candidate solution x, and we're going to find some element in that set that is less than or equal to 0. If no such element exists, we're done. Okay, because just like in the dual simplex, when we find no digression decrease, we're done. Here, once we find i.e., once we find a dual feasible solution, we're done. Here, once we find a primal feasible solution, we're done. We've solved the problem. Assuming we can't find this, though, we're going to determine an element to add to our index set and an element to subtract. So, we found the negative entry here. We're going to find an entry to add. We basically let some term v equal this term. This is actually very similar to how we added an index to the in the primal algorithm. It's equal to this thing, so it's equal to, of all the indices that are not in script j, find some v, or defined by this, that's less than or equal to 0, and find the minimum one such that this term is minimized over all these things. This is actually exactly equal to finding the minimal step size that will add a new element to the basis, and then we update our index set or our basis in this form. The details here are not important. What is important is that this form looks very, very similar to what we did in the primal algorithm, and in fact, you can derive it in the exact same way with sort of step size and all this kind of stuff. But what results in the very end is just this very simple algorithm here. Or rather, I guess it's all parts of the algorithm. Very simple iterative procedure, looking just like the simplex algorithm, but just actually operating on these dual variables, or rather in this space that maintains a dual feasible solution, whereas the primal algorithm maintains a primal feasible solution. Okay, so that's the dual simplex algorithm. Again, I'm just giving it so that you know this because it's actually quite useful in some situations. But just telling you this, it actually is not obvious why you'd want to use this, right? Because I mean, why is this any easier? Why is it any easier to find this index such that this is the case than it is just to find this? I mean, the procedure seems the same. The complexity actually is the same in general. So why would we want to use this? So in general, there actually is no reason that you want to use it. There's no real reason to prefer the dual simplex over the original simplex. Where the advantage comes is when we can easily find a dual feasible solution, but not a primal feasible solution. And importantly, this arises very often in cases where we want to incrementally add constraints to a problem. Okay, so let me talk about what I mean by this. Let's talk about a linear program in standard form. And suppose we have some set of, suppose we have the LP in standard form. So in other words, we have a problem, minimize, let me write it in black here. Minimize over x, C transpose x, subject to ax equals b, and x greater than or equal to 0. All right, and suppose I found some solution. So I know what x star is. And of course, since I solved this with the dual algorithm, I also know what, or sorry, with the simplex algorithm, not the dual simplex, just normal simplex again. I've also found some solution y. Actually, and to be clear, both primal and dual simplex will return both the primal solution and the dual solution, of course. Now suppose I want to add the constraint that in addition to these constraints, I also want to add an additional constraint G transpose X is less than or equal to H. For some vector G, this would be a vector G in Rn, and H just being a scalar. So I want to add one more constraint to my problem. Now, of course, the way we do this in standard form is that we augment our A matrix. So we have sort of like a new A matrix here. So the way we do this, right, is we translate this into G transpose X plus X n plus 1. This is a non-negative variable equals H, right? That's how we sort of do these things. And so this becomes kind of our new A matrix. This becomes our new X. We have one more term in X, and this becomes our new B matrix. Okay, so I've added one constraint to this, and I've added one inequality constraint to this, and we now have a new sort of problem in standard form. So the question is, can I find a feasible solution to this problem? Right. So obviously, if this, well, first of all, if this is already satisfied, then yes, you can. The old solution is just a feasible solution. You just pick this to be, you know, whatever the difference is there, and you found a feasible solution. Okay, so great. But the question, of course, is when this is not satisfied. If we originally, when we solved this problem here, if this thing was not satisfied for the solution that we got to that problem, then what do we do? And the short answer is I actually don't really know what we do. It's very hard in general to find a modified version of X, because you have to kind of modify potentially all the solutions X, right? You sort of have to, you know, shift all their values potentially such that they still satisfy this thing. They still satisfy all the old constraints. And they all stay non-negative, but we also satisfy this constraint too, or equivalently, we satisfy this constraint with xn plus 1 greater than or equal to 0. So how do we do that? It's not easy to do it, actually, and because it could require changing all the variables potentially. So it's not easy to see how we can modify the primal solution x to satisfy the new inequality constraint. But, and this is important, here's the critical part, it is true that we can find a new dual feasible solution really easily. So not dual optimal, right? It's not the optimal solution anymore, but it's a feasible dual solution, something that still satisfies the inequality constraint of the dual problem. And in particular, this variable here, so I'll call this like y tilde, this thing is a dual feasible solution. It's easy to see this dual feasible actually because this is our, you know, our A transpose. This is A transpose. This is our, and actually it would be, oops, go back to that. This is, oops. This is our dual feasible solution. I, of course, ended my slideshow when I end the last slide. This is our dual feasible solution. It's easy to see that this thing is now satisfied, right? Because this thing, actually would be negative this thing, if we want to be keeping exactly with the context we had before. This thing, this first one, so what is this saying? This is saying that, well, negative A transpose Y star is less than or equal to C. That is true because that was true of our old optimal solution. And the next constraint would just be that, well, our new row of our A matrix is saying that this term times this less than or equal to that. But that's just saying basically they're both 0, right? This is just saying that 0 less than or equal to 0. So in other words, this vector here is a feasible solution that satisfies the inequality constraints of our new matrix. Remember, maybe just going back one slide here. I'm going to lose my annotation because I think I ended the slideshow. But this was our augmented A tilde matrix. So this here would be our augmented A tilde matrix transposed. And of course, for that new augmented solution, this value here, y tilde, is a feasible dual solution. And therefore, we can initialize our simplex algorithm with this solution, our dual simplex, right? If we want to solve the primal, use the primal simplex method, we have to sort of start from scratch. You know, start over, maybe find an initial feasible point for this new problem, then optimize that until we find a solution. With a dual simplex, we can do what's called a warm start, where we have just slightly modified, you know, we've kept most of our dual solution. We've added one term, and we can just sort of take a few steps, hopefully, to find a new solution. So the idea is that, you know, this solution seems like it's close to the previous solution. And so in practice, you often need many, many fewer steps. And to be clear, you have to still take steps in the dual simplex, right? We only have an initial feasible point. We don't have an optimal point. But typically, because we haven't changed our solution too much, it takes many, many fewer steps, so much less time to solve than if we just start our new problem, scratch anew with a simplex method. And this notion, and this is the last thing I'll say, this idea here of adding a single, you know, solving an optimization problem where we solve a linear program, then we want to add one more constraint to that. And then, of course, that constraint is not satisfied originally, but we want to add one more constraint. That's actually exactly what we're going to come across next lecture when we talk about integer programming, where we're going to modify these linear programs exactly by adding one additional constraint at a time. And so for integer programming, it actually turns out that the dual simplex kind of can be one of the workhorses behind how you solve sort of large scale integer programs, or as large as we can really do, because it allows for this incremental solving of the linear programs. Okay, so this is actually all for our current linear programming lecture, but with this very last comment in mind, next time we're actually going to talk about integer programming, which is a very nice combination between the ideas of linear programming and the search techniques, sort of the more classical search techniques we saw in AI, even though these did not arise, integer programming techniques did not arise in the AI community. And so we'll see that next time.